Hi everyone, welcome back to another session in which we were doing deep dive into transformer models, and in this particularly we are going to deeper into what we are doing in the encoding part of the transformers architecture. And in this particular series, we are going to refer the blog of JLMR, the illustrated transformer, for understanding the architecture of transformer models. So particularly in till the last session, if you haven't watched, please go back and watch. I'll give you a very high level overview. What we are doing is for any Spanish sentence that we are trying to convert that particular sentence into an English sentence. And in that we are using transformer models for this machine translation task. And particularly on a very high level, transformer that we are using is comprising of two components, encoders and decoders. And in encoders, it might contain a stack of encoders and stack of decoders. In each of the encoder, we are having two main layers. The first is the self-attention layer, and second is the feed-forward neural network. And similarly, if we are using encoder-decoder architecture, what we are doing is we are passing the output of encoder block to the decoder block, and in particularly first we are passing the output that we want to the self-attention layer through the output of self-attention layer and the output from the encoder block. We are passing both of these into the attention layer in encoder decoder attention layer, and then finally passing it to feed forward layer, and then finally giving the output to the users. Moving forward, if we go on a very machine level, for the words that we have, it's not like even our model or even a computer understand what these words exactly means. These because these are the words of the language that we as a human has devised and understand. So particularly what a transformer or machine is doing in the back end is that for the different words that we had in a language, JSS, Achudiant, so it's converting those words into a word vector, and that particular vector is of the size 512. Generally, in the transformer models, we use the word to vec, or for converting these words into embeddings. There might be different possibilities, but here I think like they have used word to vec. In that particularly, they converted j into x1, swes into x2, and etudiant into x3. These are what we will call the word embeddings or the input word embeddings. And each of these particular vectors is of size 512. And this particular vector is kind of a unique vector to represent that and that particular word. So now what's happening in the encoder part, if we try to understand with the introduction of these input embeddings, is like we pass the input embeddings to the self-attention layer, and then after processing through the self-attention layer, we get some particular outputs z1, z2, z3, and then we pass all these outputs to the feed forward layer to processing it further. And particularly what's happening is in even in encoders, like as we discussed above, even like the encoder that we had, encoder component, it might have a stack of encoders. So particularly if we have a stack of encoders, what we might be doing is we are passing input, then self-attention layer, then Z1, Z2 output, mid output layer, then we pass those outputs to the feed forward layer, and then from that we might get output R1 and R2 that we particularly pass to another encoder block that we have. And particularly, what exactly do we like? You might have heard like attention so much time. So, what exactly do we mean by self attention? So, it's particularly giving context to the things that we have. So, for example, like they have illustrated it in a very good way through this example, in which they are mentioning the animal didn't cross the street because it was too tired. And now, if we focus on the word it, so basically what does it is in context with what was too tired. Was the street too tired? Was the animal too tired? It's as a human, it's very intuitive to for us to understand that animal it is referring, it is the animal here, and the animal was too tired. But for a machine, it's not that simple to understand. So what a self-attention is doing is it's helping the machine or the model to identify what it is referring to, what's the particular context it is, like how it and animal are. So it now in the next step in the self attention, what we are trying to find out, the Reference of it is with respect to what? Street, because, cross, animal, or what? So yeah, so if we go a little bit down and try to see what's exactly happening is, for the it token that we had, we are trying to map the relationship between all the different words that we had, and in that particularly it's saying like for the first, and if we go to the first encoder block, that the animal is much more connected to it as compared to the street. And there could be many different possibilities, but like this is what output of this particular input is mapped through this self attention loop for the encoder that we use. So now understanding, so this is what self attention might meet at a uh, grand English level, but like how when we are doing the computations, how exactly this context or this reference is being calculated, that we are going to discuss now, in which in the step of self attention in detail. So particularly, this is like it might sound a little bit confusing, but bear this thing for the next 5 minutes, and the calculations will be too much grounded and concrete for you. So particularly, what was happening is we had for example, if we take two English words in which the first word is thinking, second word is machines. Now we convert those words into embeddings, and the embeddings maybe, for example, I'll name it x1 and x2. Now, if we multiply x1 by wq, the wq is initially it's like a if we are dividing the transformer has three different parameters that we are passing: queries, key, and the value pairs. In the weight matrix of the queries that we have, in the start we are initializing it by random weights, and then we'll do backprop to get the right weights for this weights of key, queries, and values. So particularly for the word embedding that we have, we multiplied the word embedding vector by the weight matrix that we have to get the Q1, the query 1 value. Similarly, we are doing for x2 into weight of Q in, to get the query 2 value. Similarly, what we are doing is we are taking x1, then multiplying that thing by wk to get k1. And similarly for x2, we are multiplying by wk to get the k2 value. So if we see how they have done is particularly they have done something like this. And similarly for value also they did the same. They map like this, for this they map like this. Now particularly after they did the mapping, what they are trying to find out, they are trying to do like you try to understand this thing through two independent calculations, in which what's happening is from the embeddings you're getting queries and the key values, and values also. Now consider these key queries and keys as one pair and values as the second pair. From if we try to multiply the queries with keys, we get the score values. And by score, that generally the thing that we are trying to depict is like the reference of that particular word, that particular key, that particular query with the key, like how similar are they, and what's the similar, not exactly similarity, how are these refer, and what's the attention score for these particular keys that we had, keys and queries. And generally for similarity, one of the things that we do is we do the dot product, and here particularly for finding the score like Q1, K1 score, we did the dot product, and similarly we did for Q1, K2, and we are trying to find out like the which particular word has the most similarity with the query or the sentence that we had. And then moving forward from the score that we calculated, the next step what we are trying to do is divide this score. Particularly, it's I think like much more of a doing it for the stabilization step is like we will divide this score by the root of the dimension of uh, I think query that we have. So in this case, so I particularly forgot to mention. Maybe I'll mention it right now. This thing was like a 512 of the dimension 512, and the queries that we have were of the dimension 64. I think query keys were also of the same dimension. So now particularly when we are doing this thing, in this particularly, yeah, so now we are doing dividing this thing by root of 64, that is dividing by 8, so we will get the 14. And then particularly for all the values that we are getting, we are trying to apply for Q1, we are applying the softmax function. I think similarly we will do for the Q2 also. So in that particularly softmax, if you do not know, it's like I'll take exponential of this particular value divided by exponential of all the particular summation of exponential of all the different values that I have got. So in this case, if you see, go to the formula of softmax generally, it's that sum of all the probabilities will be equal to 1. And here in this particularly, we got to realize like this is the score of this particular word embedding attention, like the pair of that key and query. And particularly this has the highest, like, so what we can say on a very high level that this particular key is associated with the query that we had. So now particularly what we did is till now we haven't used the value that we had. However, we will now use that particular scores that we calculated. Yes, and so particularly now what we will do for the softmax scores that we have got, we will multiply those scores with the values that value vector that we had created earlier. And then particularly we will sum for the sum those the particular vectors that we have got. And now particular the sum vector, like if you remember from our earlier discussion, this is one of the final vectors that we have got. Now we will passing this particular vector to the feed forward layer that we had. And this particular, these are like we are getting into each and every step. Generally, in general case, these things are processed parallelly all at once for using the matrix and the vectors. And then particularly if we see, like this is what I was telling earlier, we take the word embeddings that we have multiplied by weights of the queries, then we get the query vector. Similarly, we get the key vector, and similarly, we get the value vector. And then what we did is we tried to find the similarity or the reference or the attention of that particular query with respect to that key. When we did that particular product, then we tried to scale it by dividing it up with the root of the dimensions of the key, and then finally applying a softmax on that thing to kind of try to find a score or probability. And then for that thing, the score, particular score that we got, multiplying it by the value to get the final sum that we are saying to calculate the self-attention score. This is the representation in a matrix format. Now, particularly what's happening is we calculated this particular value for one of the attention heads. For example, what I showed you earlier, we might have, this is what one attention head is. Generally in transformer model, as far as I remember, there are particularly 8 attention heads in parallel. So now we are doing these kind of calculations for 8 attention heads in parallel, and in which the weights might be randomly initialized in the sense of two. It's like sometimes the sentence that we were referring up was like the street might be referred to it and the animal might also be referred to it. So if we try to do a much more random initialization, what we are trying to see is like for the different cases are the values that we are getting much more coherent, and to find out what's the better value with a much higher score. And in that particularly how we calculate for attention head 0, we will do similarly for the attention head 1. And similarly, if we try to see like based on those things, we will get a lot of values. Like the some values that we were getting for 0, it was Z0, Z1. And similarly, we got till Z7 for the input embeddings that we had. Now, particularly what is happening is once we have calculated the Z values, the attention head values, we will concatenate all these values and then multiply it by the weight matrix that we have. And now this particular weight matrix is also having similar initialization weights and everything. And then finally, if we do that, we will get the Z matrix, which captures the information from all the different attentions head that we had. And particularly in this example, we had 8 attention heads. Now, particularly for this Z matrix that we have calculated, we will be passing this thing further into the feed-forward neural network that we have. So now trying to understand, summing up what all exactly did we discuss till now is we had particular sentence by the name thinking machines. And then we did the word embedding for each word. Now we pass those word embeddings to 8 attention layers in which each of the attention, everything everything had parallel space, and then in which we had the key query and values randomly initialized at first. We did for all the 8 attention heads that we had, and then we are calculating the key Q value pair for all the attention heads. And from key query and value, we are calculating the Z score final sum. And then we are considering all the final sums that we get, multiplying with the by the weight matrix, and then finally getting the sum or the final concatenated results, which we will pass further into the feed forward neural network that we have.